Welcome to section 5.3a, where we're going to tackle the concept of conditional probability. Now, we did a little bit of probability review at the end of Algebra 2, but this would not have been one of the topics we talked about there. So this should be brand new for you guys. So let's go ahead and learn what it means. Before we get to that, we're going to jump in with an example here, and we're looking at the Arizona Diamondbacks baseball team. And then apparently during the 2012 season, there was a kind of promotion going on by Taco Bell, where if they scored 6 or more runs in the game, then the Taco Bell would give away free tacos the next day. So we want to take those two events, whether they win or not, and whether there are tacos or not, and we want to make a little two-way table to represent this problem. So let's go ahead and practice reviewing what we did the last time. This would be a good opportunity for you guys as well to try this out now that we've practiced two-way tables a fair amount. So go ahead and fill it out for yourself while I work it out over here. I'm going to put wins going that way, tacos going this way, but it really doesn't matter which one goes each way. It looks like there were a total of 81 games altogether. They won 41, meaning they lost 40. They gave away tacos in 30. So this guy over here is going to be a 51. And then in 26 games, they did both. And from there, it's just easy math, filling out your little table. So you guys should hopefully be pretty comfortable with that because it's an important thing to be able to handle here. But we have our little two-way table representing what's happening in the problem. I didn't have to define my variables because they did it for me in the problem. So now that we have our two-way table in place, we can answer a whole bunch of questions using our information. So part B asks for the probability that the Diamondbacks win or that there are free tacos. And remember the basic idea, once you've taken the time to put this all in a little table right there, you can just count up the boxes that are good that you want, and you don't have to worry about using a formula. So you're just going to add up everything where they win or where there are tacos. So in other words, I'd want this box, I'd want this box, because these are both wins, and I'd want this box over here. If you add all three of those boxes together, it looks like that's going to be a 45. So it's going to be 45 out of all 81 of the games. You can make that a decimal and do stuff there, but that's how you would set this up. Okay? So or probability, we talked about it last time. If you make a table, you don't have to worry about overlap because everything is nicely separated in our boxes. Now, these next two problems here are going to be the new stuff that we're getting into. So when you read through this probability here in part C, it says find the probability that the Diamondbacks win given that there are free tacos. This word given is really important. This word given is a signal that we're doing something called conditional probability. Conditional probability, we'll define it on the next slide, but it's basically built under the assumption that one of your events has already occurred. So we already know for a fact in this problem, there are going to be free tacos. If I was going to write this in symbols, I'd be looking for the probability the Diamondbacks win. That was W. The symbol for given, which again I'll give you on the next page, is like a big vertical bar, and free tacos is T. So this is how I would write part C in words. Let's talk about how you would actually find it. We already know for a fact there are free tacos. It's given to us in the problem. We don't have to worry about the games without free tacos. So what we would basically do in this situation is all these not taco games over here on the right, dead to us. You can just cover up that part of the table right there. Normally on the board, I'll like scratch it out and stuff, but I have to use it again for D. So I'm not going to do that yet. What I'll do instead is I'll circle the part of the table that I actually care about. We already know there are tacos, so that games without tacos don't matter to us anymore. We're not looking at all 81 games anymore. Now we only have 30 games that we're choosing from. So there are 30 games where they got tacos, and they ask for the probability that they win. Well, that's 26 out of the 30. So basically, conditional probability in a table is pretty straightforward. You just cover up the part of the table you don't want and just do a regular probability calculation from there. And it's not too bad to set up. All right, the next one is another conditional probability. It says find the probability there are free tacos given that the Diamondbacks win their game. So if it is given that they win, we're looking for probability of tacos given win. Now we're looking at this part of the table right here because we already know for a fact that they won. These games over here where they didn't win, those don't matter to us anymore. Those are stupid. They don't care about those. We know they won. And we're looking for the probability there's going to be tacos. Well, there are 41 games that they won, and there are 26 where there were tacos. So the key takeaway with this kind of problem here is your denominator is going to change because you already know one of the events occurred. So let's formalize what we were just talking about right there and officially define a conditional probability. So conditional probability is the probability, or let's say given that one event already occurred, we're going to be finding the probability of another event. So basically, when you do conditional probability, one of the events already happens. And they'll tell you that in the problem what's already locked in, but then we're finding a new probability based on that previous example. Really simple example that I don't even have to show you guys a slide on. I'm just going to talk you through it right here. Let's say I had a bag with marbles. I had 5 blue and I had 5 red. Okay. Then I would say something like, given that my first marble was blue, if I don't put it back, what's the probability the second marble is also blue? So if it's given that the first marble is blue, that marble is already out of the bag. So when I say the answer to that, there are going to be 4 blues left out of 9 marbles. So in basic problems, you can just kind of logic your way into the answer by thinking about it. It can get more complicated though, which is why we have a formula for conditional probability. This formula is on your formula sheet here. So it's not something you have to memorize, but with probability formulas, honestly, I think you should memorize them. We use them enough that you shouldn't have to be backtracking every time we do a problem like this to look up the formula. But it is there if you are iffy on it during a quiz or something like that. So first of all, the symbol for conditional probability looks like this, and you would pronounce this the probability of A given B. The bar basically means given, and then you have your second event right there. In other words, B already happened in this problem. The way you calculate a conditional probability through a formula, you're going to find the probability of both events occurring. Both events is going to be A and B, A intersect B right here. And you're going to divide it by the probability of your second events. So in my Diamondbacks example with tacos and stuff like that, I believe what I had going on, the probability that they win the game was so let's say it was tacos given win. Win was a 41 out of 81. Tacos, I think, was 26 out of 81, if I'm not misremembering these. If you divide those, you get 26 out of 41. The 81s end up canceling out. So it's just probability of both over the probability of the one that you care about. Okay? That's basically our setup there. So let's look at a fresh example. Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there's a 90% probability that she makes it to class. However, if she does hit the snooze bar, there's a 70% probability. This 90% and this 70% are both conditional probabilities. They are conditional because we already know what happened with the snooze bar. If she doesn't hit it, there's a 90% chance. If she does hit it, there's a 70% chance. So that whether or not she hit it is already kind of wrapped into the problem. When you have a situation like this, where there's a couple of events going on, so first thing that happens is Shannon has to decide is she hitting snooze or not, and then she either makes it to school on time or she doesn't. In the last section, we talked about those nice two-way tables for probabilities. Our second probability tool, which I did talk to you guys about a little bit in Algebra 2, is making something called a tree diagram. And tree diagrams organize probability questions where you have a sequence of events going on. The first thing that's going to happen in the context of this problem is whether she doesn't hit snooze or she does. So I'm going to have no snooze. It doesn't matter what order, really. And I'm going to have snooze. And it says she hits the snooze bar on 60% of school days. So snooze is 60% of the time. That means that no snooze is 40%. These should be complements of each other. If she doesn't hit snooze, there's a 90% probability that she's on time. So there's a 90% probability she's on time, meaning that there's going to be a 10% chance that she's late. If she does hit snooze, her chances of making it on time get smaller. She's going to have a 70% probability of making it on time, and she's going to have a 30% chance of being late. So when you make a tree diagram like this second wave of probabilities right here are conditional probabilities because they're based on what happened before. So they just asked us to make a tree diagram for part A, and that's good. I got that taken care of. On the next page, they ask us for a few calculations. So the first one says, on a random day, what is the probability that she is late to class? So if you look at your tree, there are two kind of paths that Shannon could take that would result in her being late. It could be where she does not hit snooze and she's late. So it could be this path right here. That would result in her being late to school. Or she could hit snooze and she could be late. So it could be this path right here. When you go down a path in a tree diagram, you're going to multiply the probabilities together. Or you add the probabilities. This is like an and situation where you need snooze and late or something like that. You multiply your probabilities. So for the 0.4 times 0.9, this top branch, for example, would be a 0.36. That's really hard to see. So we'd have like a 0.36 up here. 0.4 times 0.10 is 0.04. 0.6, 0.7 is 0.42. And then finally 0.18. And if you add up all the end probabilities here to make sure you did it right, they should equal 1. Okay? So they asked in part B, what is the probability that she's late to class? It's a good idea to show the work. I guess I have a tree diagram, so you probably wouldn't lose credit if you didn't, but it's just smarter to show what you multiplied it in. This times this. Or it could be where she hits snooze and she's late. So you multiply the individual guys. You get this, and then it's this or this, so you just add those two things together. If you do that, you're going to get 0.22 for your answer. So good idea to show your work right here. There have been rubrics for AP problems where you would lose credit if you didn't write that down. So you got your little answer with work shown. All right, so my next problem here. Suppose that Shannon hit the snooze bar this morning. What is the probability she is late to school? This part right here, suppose she hits the snooze button this morning. That is a dressed up conditional probability. It didn't say the word given, but it does say, hey, she hit snooze. If something is locked in, you know it's a conditional probability. So if I was going to write this in symbols, I would be looking for, or using probability she is late to school, given that we already know she hit snooze. So this is the probability we're being asked to calculate. So sometimes with conditional probabilities, you can use common sense. If you look at my tree right here, it is given that she snoozed. We already know Shannon took this path right here, and she's already at this point, okay? We want to know the probability she's late. That's actually really easy. Well, if she already walked to here, and she's already made the decision she's snoozing, then she's going to be 30% of the time late. So we can just use common sense and say, the answer is 30% or 0.30 to that example. Okay? So if you're doing a conditional probability where the first part of the tree is given to you, great. All you're going to do is just write down the part that they give you at the end right here, and you're good to go. But let's talk about the last one here. And my picture is getting all kinds of messed up right now. It's hard to see. So I'm going to erase what's in red right here at least, to give myself some room to work. But for part D, it says that we are supposing that Shannon is late to school, and we want to know the probability she hits snooze. This probability, the probability of snooze given late, is not as easy to find. Late is given. But if you look at the tree, you can't just be like, oh, I'm going to walk to here in my tree. It doesn't work like that. Late is on the end and it's in a couple different spots. So if you have a situation like this, where it's the second part that's given, you have to use the formula that I gave you on the last page. And what that formula says is that you take, when you do a conditional probability, the probability of both of those things. That's the probability of snooze and late over the probability of the one that's given. And the one that's given in this problem is late. So what is the probability of snooze and late? Snooze is here. Late is here. Neither is given, just this and this. So you do 0.6 times 0.3, which is going to be a 0.18. That's the probability of snooze and late. Over the probability of late, which happens 2 different times, but I already did that up here in purple. A lot of times probability questions will make you use the answers that you've already written down. So before you start making an answer from scratch, see if it's already something you've answered. The probability of late, we already found, is a 0.22. So let me talk about what this is saying right here. Shannon's only late to school 22% of the time. So that means our denominator, our total possibilities here, is no longer 100%. We're only looking at those 22% of days where she's actually late. And then out of those 22% of days, 18% of all days are where she's actually hit snooze and is late. And if you divide these out, 0.18 divided by 0.22, that's almost 82% of the time. So if you know she was late, there's an 82% chance that she hit snooze. Okay? So that's how you work your way through a conditional probability. So let's go ahead and take a look at another problem here. Actually, we got a little ways to go here. Tree diagrams first, and just a couple of rules, and then we'll tackle our new problem. When do you multiply two probabilities together? You multiply probabilities together when it's and, or the, which not or, but and / the intersect problems, which means and. So we talked about how or problems, or is the union, you're supposed to add probabilities. When it's and or intersect, that's when you multiply your probabilities together. Is the multiplication formula on the formula sheet? No, it's not. So you do have to remember that, oh, I got to multiply them together. Now, really quickly, before I keep going with this, I see common errors with and problems once kids remember, oh, I got to multiply. If you've got two different events going on and you have to multiply them, that's great. That's what you're supposed to do with the probabilities. But if you're in two-way table lands, like earlier we were doing a problem where it was T and W like this. If they say, what's the probability of T and W, and it's in table format like this, you can just find the one that applies to both of them. So you would say it's 26 out of 81. So if you're looking at a table, use common sense and pick the one that applies to both. If you have different probabilities going on, what's the probability I roll a 6 on a die and then a 4? It'd be 1/6 times 1/6 like that. But if you have a little table, you oftentimes can just look at it and get the answer that way. But in general, you are supposed to multiply your probabilities. So our two big tools that we use for complicated probability questions are the two-way table and the tree diagram. If you see a probability question where the answer is not just there's a very good chance you're going to do one of those two things, either tree diagram or two-way table. When do you use each one? I'm going to give you a few options here. So it says, when should you use a tree diagram instead of a two-way table? Two-way tables are for or problems or problems with overlap. When should you use a tree diagram? When you have conditional probabilities, that can be a giveaway. So like Shannon, her snooze, like that affected how late to school she was or how often she was late to school. Or more frequently, or probably easier to remember, when you have sequential events. What do I mean by that? One thing has to happen before the other. So Shannon had to decide if she was going to snooze or not before she was late to school or not. So if there's a clear order to how your events happen, a tree diagram is what you're going to want to use. So those are going to be our two big strategies here. All right, so we have a big problem to kind of finish off our slides here where we'll get to practice what we've been talking about. So a lot of employers require that employees take drug tests before they start working. And there's such a thing as a false positive and a false negative. So if a test comes back positive, if you take a drug test and it comes back positive, that means the test says there are drugs in this person's system. Positive means they found drugs in your system. Negative means that they did not find drugs in your system. It's the same thing with like diagnoses of stuff like that. If you test positive for an illness, you have the illness. But then there's a false positive and a false negative. So if you think just logically about what that means, a false positive means the test said positive, but it was wrong. So the test said, hey, you did drugs when you actually didn't. And a false negative would mean, hey, the test comes back, says, yeah, this person's good, they don't do drugs, but they actually did. So you have to kind of think in your head through the words right there. When you talk about like a false positive, there's a hidden conditional probability in that statement. If you say false positive, what's assumed or what's given in the problem? Well, the test said positive, but the person was actually negative. So it's given that the person was negative. What's the probability the test says positive? So anyway, these are hidden conditional probabilities right here. So what we're going to have to do with this problem, it doesn't say, oh, make a tree diagram, but it would be logical to do so. It says 4% of employees use drugs, and then you're going to take a test which has false positive and false negative rates. The first thing that's going to happen, if you think about this sequence of things right here, the employee is either going to do drugs or they're not. So that's going to happen before the test comes into play. So the first thing we would want to branch off for is whether or not the employee does drugs. And it says that that happens in 4% of the time. Our problems today with our tree diagrams have only had two possibilities here. It's very possible you could have a tree where there are 3 or 4 options. The key is that all the branches along the same like little bend right here have to add up to 1. All right, so after you do drugs or you don't do drugs, you're going to take a test. And the test is either going to come back positive or the test is going to come back negative. I'm going to work the false positive and false negative into things when I actually write down where the numbers go. But you're going to do drugs or not, your test is going to come back positive or it's going to come back negative. If you do drugs and the test comes back positive, that's not a false anything. That's the test making the right call. But if you do drugs and the test comes back negative, think about what that would be. Is that a false positive or is that a false negative? It is a false negative for this part. So there's a 10% chance that if you do drugs, the test isn't going to catch you. That means there's a 90% chance it will correctly catch you. And then a false positive, that means no drugs, but it says you did drugs. That's 0.05, meaning this guy down here, negative like it's supposed to, is 0.95. And what I'm going to do is I'm going to multiply along my paths right here and get all my little probabilities for the end. 0.4 times 0.9 is a 0.36. Sometimes it's helpful. If you don't want to show that work later, you can just show it like right here. So I can do 0.4 times 0.10 is 0.04. As long as the work is somewhere on your problem, you're in pretty good shape. 0.96 times 0.05 is 0.048. And then 0.96 times 0.95 is 0.912. So now that I have my little tree worked out, I can actually answer the question they asked me, which is what is the probability a person will test positive? So that could be this path right here. And it could also be, oh, shoot, my probability was off on this one. I'm glad I caught it early and not late. 0.04 times 0.9 is 0.036. I was off by a decimal spot there. That's also a 0.04. So I screwed those up as I was going through here. This is going to be 0.004. Glad I caught it sooner rather than later. Sorry about that. So we've got our new adjusted probabilities here. Anyway, we were finding probability of positive, which is going to be the one I have circled and also this one over here. All right. So when you look at these two probabilities, what's actually kind of crazy right here, we're about to find the answer for this one. There's a 0.036 chance, 3.6% chance that a person did drugs and test positive. There is a 0.048 chance that a person didn't do drugs and came back positive. So if you think about what that's saying, if you get a positive test, it's actually, crazily enough, more likely that you didn't do drugs than that you did in this problem. Okay? Why does that make any sense at all? That's so crazy. Like, why would it be more likely if you test positive that you actually didn't do drugs? It has to do with the weights of your different groups right here. Most people fell into this no drug category on the way that the problem was structured right here. So 5% of a big number is going to be more than 90% of a small number. So if your groups are fairly different in size, you can actually have stuff like that happen. So if you get a positive test, like in a situation like this, and you didn't do drugs, ask for a second test, like how do you fix it? You take a second test and that one should clear you, okay? So that's actually kind of crazy that if you think about it, that it's more likely your positive test would mean you didn't do drugs. So what percent of prospective employees who test positive actually do drugs? I assume that's what that says here. It's covered under that. But it's kind of what we were talking about right here. This is a hidden conditional probability. It's the probability who test positive actually do drugs. So we want to find out the probability that you do drugs given that you test positive. So we know already that they test positive. What I would do for this is I would take the probability of both drugs and positive, which is 0.036. This times this is 0.036. And I would take that out of 0.084. So if I actually divide these right here, I'm basically just figuring out what percent of the positive tests are people who did drugs. And the answer to that is 0.429 if you actually round your answer right there. So as I said, if you get a positive test, it's actually more likely still that you didn't do drugs just because of those false positives and false negatives. When companies are figuring out like how sensitive their test is going to be, they have to take that into account, false positives and false negatives, because if they move it too far one way where it's too sensitive, you're going to have more of one type of error, where if they make it less sensitive, you have more of the other. This plays into stuff we'll talk about more second semester, but that idea of a false positive or false negative, basically, if you're ever in a situation where you're getting tested for an illness or tested for drugs or whatever it is, and the test comes back wrong, or like you're not thinking the result is correct, that's why they would have you do a second test to make sure that's still the case.